Hi students, my name is Malindri Eastes and I am obviously a mathematics teacher. We are going to look at Maths Olympiad type questions involving patterns and sequences today. Let's jump straight into it.
Before we jump into some Maths Olympiad questions on sequences, I want to first share a few very useful formula with you that might make your life a lot easier and to solve these kinds of problems quicker. The first pattern that we are going to have a look at is called the arithmetic sequence, or we also call this the linear sequence. This might seem familiar. This sequence is not new to your syllabus. You might have covered this already at school level. So the linear sequence is not a new sequence for you. At this stage, you should know that a linear sequence will always have a constant difference. So the meaning is basically either you're going to add something consistently or you are going to subtract something consistently, and that will give you a common difference every single time. Now, a very common question to this is to find the formula of the sequence. They also call it the nth term. Now, if you look at the term numbers, so I just rewrote the pattern here. Number 3 is actually my first term, so I call it term 1. And then term 2 will be my number 7. So if you want to find the formula links the pattern's position to the pattern's value. So we call this the pattern's position, and we call that the pattern's value. And the formula helps you to get to the value of the pattern if you have the position. So a very quick way to do this, especially if you've got a linear sequence, is to work out the common difference first. And we already did that earlier. So my constant difference in this case is 4. Now you'll see that we always start with the formula using Tn as my first variable. Now Tn, this whole position here, let me just rewrite this. So Tn represents the value of the term. The value of the term, we also call it the output variable. So as soon as you put in your position into the formula, so where you are, if you work out the formula, you get the value of the sequence. So this is the position. Okay, this is the term number that you want to sub in there and get your answer out. Now, a very quick way to get to that formula, I know that formula is written down there, but most of the time they want you to find it. So what we do is, we always start with Tn. We first find the common difference, and the common difference is always times by n. Always. So it's basically your d times by n. And then you want to do a small little test. So you want to kind of go and sub in your term position to see what your answer is. So if my first term, that means my n will be 1, then my first answer for this, if I sub 1 into n, is actually 4. So this is saying at this stage, if my first term is subbed into n, my answer is 4. Now that is actually not true, because if you look at your first term is not 4, your first term is 3. So you need to figure out, what do I do with this 4 to get it to a 3? And what we do there is we subtract 1, and that's why minus 1 is then part of your formula. You can also test it with the second term. So let's do this again, just so that you are clear on this nice and quick and easy way of finding the formula. So you've got your 4n. Remember, you always take your common difference and you times it with n. Then let's test the second term. So if I sub in 2 there, I will get 4 times 2. So my second term will be 8. This is what this is saying. Term 2 is 8. But is that true? No. Term 2 is not 8. We have to subtract 1 to get to 7. So that's why I need to subtract 1 from the formula so that the formula works. So that is a very quick way to get to the formula. But if you forget how that whole method works, then you can also study another formula for me, and that is the one mentioned here. Okay, so this is just a formula to memorize. You will also see this formula again in grade 10, 11, and 12. We use this formula until you leave school. So if you can memorize it now, it will make your life a lot easier. Again, just going over this formula, what is each of these variables? What do they mean? Tn, by now we know that this is the value of the term. A is always represented by the first term of the sequence. N is the position of the term, so this is where you will find your term. And then finally your D at the back is your common difference. So just using this formula to show you how you get to your final formula for this sequence. Now the sequence I'm looking at, I'm just going to write it down again, is 3, 7, and we said 11 and 15. Okay, so that's the sequence that I want to find the formula of by using the actual formula for the arithmetic sequence. Now Tn stays Tn. You don't want to sub in anything here at the moment. Then your first term is going to be 3. N minus 1, you don't want to sub anything into n at the moment because we want the formula, and then you sub in your common difference. So the common difference and your first term will be the only two values that you will need to get to your formula. And then you can see here, you are timesing into the bracket, and 3 minus 4 is minus 1, and you end up with the same formula. So 4n minus 1, Tn is equal to 4n minus 1 is then your final nth term or your sequences formula. It's a little bit more steps than the first method, so you can decide which method you want to use in the Olympiads or in your exams. Then a very useful formula, if you have the value of the last term and you want to know, and you want to know, let's just fix this, how many terms you have. So there's a example for you. The first term is given as 12. The second term is 10. So you can see that you are subtracting 2 every time. So this is an arithmetic sequence. I am subtracting with a constant value every time. And then they give us the last term. So the last term of this sequence is minus 8. And I want to know how many terms do we have here. We know that we are starting with term 1. This is term 2. That's term 3. But my last term, which we always call Tn, we do not have that position. We don't know which term this is. So that's why we are calling it n. Now, there's a very quick way to do this. And to get you to that formula, I just want to show you what I'm using. I'm actually using the formula that we used earlier. But instead of writing Tn in front, I'm calling Tn my last term. So I'm calling it L. So my last term is now L. My first term is A. And my constant difference is D. Now, if I sub in all of those values, I know that my last term is minus 8. My first term is 12. And that my common difference is negative 2. If you multiply that into your bracket, then you can simplify that quite nicely to get n's answer. So you can see that it's going to be the 11th term. So the 11th term is going to be the last term of a value of minus 8. So that is what you've just found. Now, a quick way to rearrange this formula is to start off with what we had. You can then see I'm taking the first term to the left-hand side. So this is the last term minus the first term. Then I'm going to divide by the common difference. And then finally, I'm going to take this 1 to the other side. So this is a very useful formula to remember. If you want the amount of terms and you have your last term, you've got your first term, and you've got your common difference, then this you need to memorize. So it's 1 plus the last minus the first divided by the difference, and you will get your amount of terms. Very easy. Then finally, one more formula that I need to discuss when it comes to arithmetic sequences is the sum of an arithmetic sequence. There's a formula that you can use to get to the sum of a certain amount of terms. Now, I'm going to show you where this formula comes from. This is also not in your syllabus at this stage. You will see this formula later on in grade 12 and 11. So do not worry about that too much now. But if you can memorize this for Maths Olympiads, it will make your life a lot easier. So what we've got here at the top is the sum of. So I'm using S just to say I am adding my terms together. And you will see here that I'm starting with A. The A is my first term. My second term in blue here, I'm adding my common difference. So my second term is my first term plus my common difference. My third term is in green, where it's the first term plus a common difference plus another common difference. So that's going to be A plus 2D. And you can go on like that forever. And we know that our last term in our sequence, remember, this is represented by Tn. Okay, so Tn's formula, this is the last term of the sequence, is the formula that we did earlier, A plus n minus 1 times D. So this is the formula for a normal arithmetic sequence, or a linear sequence if you want. So let's just erase that little bit there. Right, now what I'm going to do now is I'm going to take this exact same expression or sum, and I'm going to write it out again, but I'm going to start with the last term and then end up with the first term being the last one. So I'm just rearranging it. So just as you can see here, I'll just draw an arrow. You can see that my last term is now my first term. And my second last term is now my second term. And I write that out, and then my first term here is now my last term at the end. And finally, we are now going to add. So we add these two sums together, but we add them vertically. So you'll see here, I did it here for you. So the sum n plus another sum n is going to be 2 sum n's. So it's almost like saying x plus x is 2x. I'm just keeping Sn the same. Then if I'm adding these two first terms together, a plus a is 2a, and you just bring that down. So this is going to be my first term. And that will go on forever. So you can see that formula is repeated everywhere. We just don't know how many times. That's why we are calling it n. It's going on forever and ever and ever. So finally, we are now at that formula. All we need to do is to get Sn alone. So we are going to divide by 2 later on, but also we need to know how many of these do we have. You see, it's 2a plus n minus 1d, and then another one, and then another. So we know that we've got n terms. There's n terms many because it goes on forever and ever. So instead of writing all of them out, I can just say that formula that is repeating itself times n, because that's how many terms there are. And then finally, you divide that by 2, divide both sides by 2, to get Sn alone, and that is the formula for the sum of an arithmetic sequence. This is a very useful formula that you can use. So if you are adding a few terms together, and that sequence, and we actually call it a series now. So if you are adding a sequence, it becomes a series. So let me show you an example. There's an example for you. So 3 plus 5 plus 7. So you can see I am adding with 2 every time. So it is an arithmetic sequence, but because I'm adding them, it now becomes an arithmetic series. And they can ask you, what is the sum of this series up to 24 terms? What is the sum? The sum of 24 terms. So if I'm going to add all of these terms together 24 times, what is my answer? And that's where the formula at the top becomes quite useful, because the sum of 24 terms, your n is now 24, and you sub that into n. So 24 is n, your a, remember this is your first term, so that's 3 there. So 3 is your first term. 23, how did I get to that? That's n minus 1. And remember, n was 24. So 24 minus 1 is 23. And this is your common difference. Common difference in this case is plus 2. And if you plug that in your calculator, or you can just work it out quickly. Obviously, in the Maths Olympiads, you don't have a calculator, but this is very easy to work out, and you will get 624. So this is just a very quick way of getting to the sum of a linear sequence. Okay, useful? Please try and memorize it. Then the final pattern that we are going to have a look at is called the geometric pattern. Geometric pattern. Now, this pattern, I think you are only going to be introduced to in grade 9. Some of you might have seen the geometric pattern already introduced in grade 8. So there is a very specific formula for this type of pattern, and it is completely different to the linear sequence. Now, if you look at the example that I've got here, 2, 6, 18, to get from the first term to the second term to the third term, you can see that I am timesing by 3. So the big difference here is that with the geometric pattern, I am multiplying with a constant value. And to test that, to test if you've got a geometric pattern, you can say term 2 divided by term 1, 6 divided by 2 gives you 3, then take term 3 divided by term 2, and you should get the same answer. And if you get the same answer, you can now say, yes, I've got a common ratio. I've got a common ratio, and we say that is represented by R. So there's also a formula for the sequence, and I want to show you where this formula actually comes from. So I took the pattern that I wrote out here at the top, and I'm writing it out in a slightly different way. So you'll see here, I said term 1 is equal to 2 times 3 to the power 0. Now remember, 3 to the power 0 is actually just 1. Anything in the world to the power 0 is 1, so 2 times 1 is 2. So my first term was 2. Then I took my first term and I times it by 3. 2 times 3 is 6. I then take that and times it by another 3 to get to the next term, and I times it by another 3 to get to the fourth term. Now, if I write this as exponents, I did this here on the side, you can see that the formula here to get to the first term is 2 times 3 to the power 0. Then to get to the second term, 2 times 3 to the power 1, and so forth and so forth. Now, what I need you to see here is that the position of the term 2 becomes 1 less in the exponent. Position 3, exponent 2. Position 4, exponent 3. So the formula looks like this. Formula for the arithmetic sequence. You've got your first term. A is always your first term. And then R here is your common ratio. So what you are timesing by. And I am going to take my exponent and subtract 1 from it every single time. So whatever my position is, subtracting it by 1, and that is my exponent. Very useful formula to remember. You do not have to know how you derive it or how you get to it. If you can just memorize it, you can use it quick and easily. Then the last formula that we need to discuss is the formula for the sum of a geometric series. So this is when I've got a geometric sequence And I am adding those terms together to get to a value for the sum as I'm adding. Now, to show you where this formula comes from, again, the derivation of this formula, how I'm getting to the formulas is not important. You do not have to know that, but it is useful to know where it comes from. You know, these formulas don't just fall out of the air. So it just gives you a little bit of insight on why we can use these formulas so nicely. So the first sum that I wrote out for you is the sum of a normal geometric series. So you can see I'm starting with the first term. In this case, the first term is A. A is always your first term, whether you are working with a geometric or linear sequence. And then I'm timesing by my common ratio to get to my second term. And I'm doing that all the time. So I'm timesing by R to get to each of these terms. And then my last term, as we know, is also called my Tnth term, and that is represented by the geometric sequence formula that we just saw at the top. And then for my second equation that I'm going to write out here is I'm going to take the same sum that I've just written out, and I'm going to times everything by another ratio, by R. So the left-hand side will be times by R, then my first term is going to be times by R, and all of these gets another R added to it. Not added to it, but multiplied to it. And then I line them up a bit. So I take the first equation, wrote it out. I took the second equation, and I'm just lining them up slightly differently. So you can see here, AR there is the same as that AR. So I'm just going to write them underneath each other. So you can see there's a gap there for the first term of the second equation. Lining up all the like terms if you want. All the like terms are underneath each other. And then I subtract the whole second equation. So how this works is we're going to say the sum n, Sn, minus r, Sn. So I just wrote that out. So sum n minus r, Sn. So that's the left-hand side of the equation after my subtraction. Now this is quite nice. You can see that all the like terms will actually cancel. You've got AR minus AR. AR squared minus AR squared. So all of these cancel out. Every single one of them. All of them. And then the only one that you've got left would be this one at the back. That one doesn't pair up. So you've got A left, which is this A, minus, because this is now, there's nothing there, so that's actually 0 minus ARN, so that's just minus ARN. And then to get your Sn alone, there's just some manipulation that takes place here. We're going to take out an Sn there as a highest common factor. So we write that outside with a bracket 1 minus r. And we do the same on the right hand side. We take A out as a highest common factor, and we've got 1 minus r to the power n left. And finally, to get Sn alone, we divide the left hand side by this bracket. So if we divide the left, we have to also divide the right, and we get the formula. So this is your final formula for the sum of a geometric series. So how do we use this? Just a quick example. 2 plus 6 plus 18. This is a geometric series. I am timesing by 3 every time. So if I want the sum of this sequence or this series up to 18 terms, if I use the formula at the top, sum of 18, the first term is 2. My common ratio is 3. And finally, how many terms do I have? 18. And if you plug that in the calculator, it's going to be one massive answer. Again, you do not have your calculator in the Maths Olympiads, so you will have to try and work this out as far as you possibly can, maybe leaving it in exponent form. So you can see the 2's will cancel there. So you're going to get negative 1, 1 minus 3 to the power 18. And finally, simplest answer here is just to say it's negative 1 plus 3 to the power 18. and you can leave it like that, especially if the exponent is very big. That answer is way too big to write out. So that would be your sum of 18 terms. All right, so those are all the very useful formula when it comes to sequences. Now we can jump to the actual question. So let's go and look at the first one. I wrote down the integers 25, 26, 27 all the way to 208. How many digits did I write down? Now, I know that I'm starting with a 2-digit number at 25, so I need to kind of figure out how many 2-digit numbers will I have. So if you look at all the 2-digit numbers between 25 and then obviously 99 would be the last 2-digit number in that sequence, all of them will have 2 digits. So we just need to figure out how many numbers are there between 25 and 99. Now there's a very quick way to get the amount of numbers. You can just take the last number minus the first number plus 1. Now, how that works, let me just quickly give you an example. So if I've got 1, 2, 3, 4, 5, those are my numbers. How many numbers do we have? Quick way to get that is to say 5 minus 1 plus 1. So 5 minus 1 is 4, plus 1 is 5 numbers, and you can see that's 1, 2, 3, 4, 5 numbers. This little formula always works. So that's what I used here. I said 99 minus 25 plus 1 gives me 75 numbers. So I know that there's going to be 75 2-digit numbers. So already I know it's 75 times 2 because I need to count the amount of digits. So 75 times 2 is going to give me 150 digits. Then I need to worry about all the numbers from 100 to 208. So I want to know how many numbers are there between 100 and 208. So again, I'm going to say 208 minus 100 plus 1. That gives me 109 numbers. And all of these numbers have 3 digits. So we're going to say 109 times 3 gives me 327 digits. And then I add all these digits together to get the total sum of all the digits that I am using. So your final answer for this one is 477 digits in total. The sum of the first 3 terms in an increasing arithmetic sequence is 12. And the product of the first 3 terms is minus 80. Find the third term. Now, we just had a very long discussion about the arithmetic sequence, which is also called the linear sequence. And we saw that there is a way that we can represent a linear sequence if we do not know what the values are. You know, if we don't know what the first term is and we don't know what the common difference is, we can represent this sequence by using A and by using D. So my first term, you can say, is called A, and my second term is called A plus D, and my third term is called A plus 2D. Now, I am not going to use this exact same expression because there's a quicker way to get to this. I'm going to use the same kind of idea, but I'm going to make my second term, I am going to call that A. So I did not start with A as my first term. I'm going to call my middle term A, or let's say my second term. Okay, so my middle term is A. If I am going back with the common difference, or if I'm going ahead with the common difference, so if I add the common difference or subtract the common difference, I can get to the term before A, and I can get to the term after A. So it's almost the same kind of principle as what we used earlier, but slightly differently. The reason for that is, if I write it as what I have here, and I add these terms together, And I know that the sum of the first three terms of the sequence, or the sum of the first three terms is 12. That's what the question said. Then if I add all the a's together, that's going to give me 3a. And then if I add all the d's, you will see that the d's cancel. So immediately one of your variables are gone. We are eliminating it, and you can get to your first term quite easily. Very quick. Now, just to go back, if you had to use this formula, it's not wrong. So if you wanted to say, a plus d plus a plus 2d, all of that is equal to 12. The problem is you are still going to end up with two variables. And then you'll have to find another equation with two variables so that you can solve them simultaneously, and then the algebra just becomes intense. So it is just quicker to go this route. Nice and easy, you get your first term and you are done. Then to get your common difference, we use the second scenario. So if you just go up to the question, they say the product of the first three terms is minus 80. Okay, so the product of the first three terms, now I'm using the same 3 that I used earlier, and I'm going to times them all, and I then get minus 80. So if I times this out, you can see that I found 4. A is 4, which is, and remember now, in this case, A is not your first term. A is your middle term. But because you are using the same representation of what you used earlier, A is still your middle term. So that's not a problem. So don't get confused here. If you sub your 4 in, you want to now multiply out these brackets. So this is going to be a FOIL question. So I'm just doing it here on the side. I did this quite quickly. You can see that if you times this out using FOIL, you can also just do that in a quick way, because you can see this is actually difference of squares backwards. So, but if you do this in the long way, let me do it for the grade 7s. If there are any grade 7s listening to this, you will not know what FOIL means. So what I'm actually doing is I'm timesing every single term with every single term in the second bracket. So I'm saying 4 times 4 is 16. 4 times minus d times 4 is minus 4d. 4 times d is plus 4d. And then the last one is minus d times plus d is minus d squared. And then you'll see that the middle terms actually cancel, and you just get 16 minus d squared, and that's where I got this from. So that 4 is that 4 in front, times out the brackets. Then I divided by 4 here to get negative 20 on the right hand side. Subtracted 16, got negative 36. The negatives cancel. You then take the square root. Now just be careful here. Whenever you take a square root, your answer on the right hand side might have two different values. It might be a plus or it might be a minus. You have two answers there. But in our scenario, in this question, my constant difference will be a positive, because if you go back to the question, it says there, this is an increasing arithmetic sequence. So we have to go up. And to go up, we need to add. We can't subtract a number. So your constant difference is 6. And then you've got your answer. So find the third term. So we just need to quickly work that out. So the third term, remember now, you started off with your middle term. Your middle term you called A. Then your first term was A minus D, and your third term was A plus D. So this was your term 1, term 2, and term 3. So they want this answer. So you are just going to say, okay, well, my middle term was 4 plus 6. So my third term is 10. And you've answered the question. for how many positive values of n are both a half times n and 2n, or 2 times n, a 2-digit integer answer. So we are going to look at a half n first, and what I want to try and find out is what do I need to multiply a half with to get a 2-digit number. Now if you think about that, for a half n to be a 2-digit number answer, the answer needs to be at least equal to 10, because this is your smallest 2-digit number that you can get in the world. So if you set a half n equal to 10, which is your least possible, smallest possible answer that will be viable for this scenario to play out, that means that n in that case must be at least 20. So you can't go lower than 20 for n. So that's the first thing that we can figure out there. But in the same instance, a half n must also be an integer. I'm just going back to the question. They say there it must be a 2-digit integer, the answer itself. So if you look at a half n, and a half n must be an integer answer, it means that whatever I'm going to sub in this space must be an even number for you not to get any decimals out. So then it means that your lowest possible value for n, we know, is 20, we saw that, and then the highest possible value for n would be at most 198, because as soon as you go beyond that, so if you've got a half times 200, for instance, you will get a 3-digit answer, and this is not allowed. If you take a half times 199, then again you don't get an integer. So for this scenario, 198 is going to be your biggest possible answer. But now I also need to consider the answer for 2n. Now on the right hand side here, I investigated what's going to happen if I times something with 2. And remember, I want an answer of a 2-digit number. So to get a 2-digit number as an answer, the biggest possible 2-digit number that I can get in the world is 99. So if I then take my 2n and I set it equal to that biggest possible 2-digit number, it means that my n value in that scenario must be 49,5. And that's the highest possible n that will work for this scenario to play out correctly. And then if you look at the smallest possible 2-digit number, which is a 10 again, if I set 2n equal to 10, then this is saying the lowest possible n that can work for this scenario is going to be 5. So if you look at your let's say your interval here, n needs to lie between 5 and 49,5, but now you need to decide on an interval that will connect both of these scenarios together. So which numbers will work for both scenarios? Now we saw in the first scenario that n's lowest possible value must be 20. It means that n cannot be lower than 20. So that discards the 5 immediately. So we know that we have to start at 20. Then for the highest possible value, for this one, it's 49,5. So I cannot go higher than 49,5. So if you go to your interval here on the left-hand side, that discards the 198 immediately because that is already bigger than 49,5. But 49,5 is not an integer. Or an even number. Sorry, 49,5 is not an even number. You see, n must be even. We saw that there in the first scenario there. So we know that we have to go and find out how many numbers do we have that are even between 20 which is my lowest possible value for n, and then my highest possible value for n that can work for both of these intervals or for both of these scenarios to play out would be 48. So how many numbers are even between 20 and 48? And to figure that out, you can actually just create a new pattern. So I started my term 1 at 20, and you can see that I'm writing out all of my even numbers, and I'm stopping at 48. So I know that the common difference here is plus 2. I know that my last term is 48. So I set my formula equal to 48. I plug in my first term of 20. I know that my common difference is 2. Quickly multiply that out, and you then get your answer. So there's going to be 15 numbers that will work for n to make both of these criteria or scenarios play out correctly. The decimal form of 3 divided by 7 is the recurring decimal 0,428571, 428571. What is the digit in the 2014th position or place? Now, this is a very common question in Maths Olympiads, and you need to kind of check out what is the pattern and what are the groups what is the group pattern that is repeated. So I tried to write that out for you here at the bottom. You can see the 428571. Those 6 numbers are repeated every single time. So it's a group of 6 that is repeated into infinity. Now what we need to figure out is how many full groups of 6s do I have in 2014 terms. So how many times can 6 go into 2014? And that actually can't happen. So if you take 2014 and divide it by 6, you get an ugly answer with a remainder. So obviously 6 can't divide perfectly into 2014. So you need to figure out what is the closest number to 2014 that will be divisible by 6. And you can go one back obviously, so 2013 divided by 6, 2012 divided by 6, but you won't get answers. The only one closest to 2014 that will be divisible by 6 is 2010. So 2010 is exactly divisible by 6. Now what does this mean? It means that the 2010th digit will be the last number in the group of 6, and the last number in this group of 6 is a 1. Now I wrote this out for you just to show you what I'm saying here. So that's 428571. That's the pattern. That's the 6 numbers that are repeated, and I just figured out that the 2010th digit will be the number 1 because it will be a full group of 6 that is repeated in that amount of terms. So we need to figure out, how many terms are left. So from 2014 we've got 1, 2, 3, 4 digits or 4 positions to get to the 2014th position. So now remember, this pattern is going to keep on repeating itself. So after the 6th number in the group of 6, I'm going to start again. So this is going to be 4285. So I can see from this that my 2014th digit is going to be the number 5. A very common question in Maths Olympiads. Find the last 2 digits of 6 to the power 2014. Now, when you get questions like these, where your exponents are massive, what you want to try and do first is to see a pattern. You want to start with 6 to the power 1, 6 to the power 2, and you want to go and work out and see if there's some numbers that are repeated in certain positions. Now, in this question, we are only interested in the last 2 digits of the answer. So if we get to 6 to the power 4, you don't have a calculator with you, so you really do not have to go and work out what is 6 to the power 4. You can just work out what will be the last 2 digits. So take the last digit from your previous answer and times that with the last 2 digits of the next. So let me just explain that quickly. You can see I've started writing this out. So 6 to the power 1 is 6. 6 to the power 2, that's still easy, 36. 6 to the power 3 is 216. That's also still easy to multiply out without a calculator. But after this, it becomes quite interesting. So to get the next 2 last digits, what we do is we take these 2 last digits, 16, and we times that by 6. So 16 times 6, if you work that out, is 96. So your last 2 digits in this number, which these are the only 2 I'm really interested in, is going to be 96. Then for the next one, I take 96 and I times that by my previous last digit. So 96 times 6, that gives me 576. But I'm only interested in the last 2, you see. So the last 2 is going to be 76. And you keep on doing that. So you say, in the next one, you're going to take 6. And you're going to times that by 76. And then you're going to take 6 and you're going to times 56. You can see I did that here on the side. So you can see your last digits, your last 2 digits are the only 2 that you are interested in. And finally, when you get to 6 to the power 7, guys, your 56 times 6 gives you 36 as your last digit. So you can see here, when your exponent is 2, you get 36. And when your exponent is a 7, you also get 36 as your last digits. So that is the pattern. That 36 is going to be repeated, but now I just need to check if this pattern works out. So will this fall onto a 2 and a 7 for the next 10? So what I mean is, if you are going to go to 6 to the power 12, do you also get a 36 at the back? And you do, because you can see here, we are adding 5 every time. From 2 to 7, there's 5. Okay, so the common difference is 5. And if you add 5 to 7, you get 12 again. And if you take 12 and you add 5, you get 17. So it keeps on falling on the same position in each group of 10. So 2, 7, 12, 17, 22, 27. So from that pattern, it's quite easy to see that 2012, remember now, we want the last 2 digits of the 2014th exponent, 6 to the power 2014. But we know that 6 to the power 2012, because it ends with a 2, those 2 last digits will definitely be 36, because that's what the pattern is telling me at the top. So that 36, and breaking up 2014, I can break that up by saying that's 6 to the power 2012 times 6 squared. You see, if I add these 2 exponents together, I'm going to get 2014 anyway. And we know that the last 2 digits here is going to be 36. Let's just put that in. So that's going to be 36, the last 2 digits. And we know that these 2, 6 squared is 36. And if we times 36 with 36, the last 2 terms there is going to be 96. So the trick with this is to go and find a pattern. Find a repeat for what you are looking at, and then go and find a pattern on how to get to your final answer. Calculate the value of the following, and we've got some kind of sequence happening there, and you can see that we are first subtracting, then adding, then subtracting. And sure, looking at that at first, it might seem a bit impossible to do, but if you stay calm and breathe, you can actually see that there is something happening here. 2013 minus 2009 is going to give you 4 as an answer. And the same with the next and the same with the next. So what I did here for you is to group them. So I took the first two, put a bracket around them to say that, if I look at these two together, that's almost like my first term, if you want. That answer is going to be 4. And the next answer is going to be 4, which means this last one is also going to be 4. So I know that I'm getting answers of 4 everywhere. My mission is to find out how many 4s do I have, because you see I'm skipping quite a lot of brackets here, quite a lot of pairs that I don't know. So I need to figure out how many 4s do I have in the sequence. Now the quickest way to do this is to look at the first term in every bracket. You see, the first term in every bracket will be the same amount of 4s in every bracket. So if that is term 1, that is going to be my first 4. If that is term 2, I now have 2 4s. So we just need to figure out how many of these first terms do we have. And those first terms is actually a sequence by itself. 2013, 2005, and 29. So if you write that down, there it is, 2013, 2005, 1997, and it ends up with 29. I want to know how many of them are there. How many of these terms do we have? Now we have a very quick formula that can help us with this. We've got the last, we've got the first, and we have the common difference. Common difference here is minus 8. So how many terms do I have? There's my formula. 1 plus the last term minus the first term. Divide that by the common difference. That gives me 249 terms. So that's the amount of terms that I have, which means this is the amount of 4s that I have. So what's the answer then? It's 249 times 4 gives me 996. Very nice and easy way of doing this. Derive a formula for the sum of all proper factors of p to the power n, where p is a prime number. A proper factor is one that is different from itself. So to explain what they are actually saying here, I'm just going to show you 2 examples. In the first example here, I took a base of 4. You can see 4 is just a number. It's not a prime number. And if I say, let's raise it to the power of 3, that answer is going to give me 64. Now, if I have to write out all the factors of 64, you will have quite a few, but you will have 1. 1 will be a factor of 64. You will have 4 to the power 1, 4 squared, and 4 cubed. So you can see that what I'm doing here is I'm taking the base that I used, in this case it's 4, and I'm going up in powers of, up to the maximum exponent that I'm actually looking at there. And all of these answers here, 4 to the power 0, 1, and 4, and 16, they will all be factors of 64. The problem is that they are not the only factors of 64. You also get, for instance, 8, and you get 32. That's not part of this pattern that you do get. But if I change this base to a prime number, so in this example, I'm using 7 and I'm cubing 7. Now, if I cube 7, I get an answer of 343. Now, if I have to write out all the factors of 343, you will see that continuing this pattern, you can also go up in powers of 7 and go up to the highest exponent that's used here. So for instance, I would start at 7 to the power 0, 7 to the power 1, 7 squared, and 7 cubed. Now, if you work all of this out, you get 1, you get 7, you get 49, and 7 cubed is 3,343. Now, what's interesting about this is that if you go and work out all the factors of 343, these are going to be the only factors that exists for that number. There won't be any others that does not follow this pattern, the specific one. And the reason for that is because your base that you are using is a prime number. So that is the significance that we are seeing here. Now, if you do use that pattern to describe what's happening here, you can see that I am just using P for my base. I know that P is a prime number like 7. And if I'm going to add up all the factors, it's going to follow that pattern, and there won't be any other factors to worry about except the prime number and going up in consecutive exponents up to your maximum exponent that you are using. So you can see there I'm adding all of them, so P to the power 1 plus P squared plus P cubed up to whatever your maximum exponent is. So they want to know, what is the formula for the sum of this? Now, looking at this pattern or this series, because this pattern is now added together, I can see that this is a geometric pattern. How do I know that? Because I am timesing by P with every single term in this sequence. So if I am multiplying with something every time, geometric sequence. So now I want the sum of a geometric sequence or series, and there you've got it. This is the formula that we've done earlier. So A is your first term, and in this case, A is going to be 1. Your ratio is what you are timesing by every time, and in this case, that is going to be P. And once you sub that into the formula, you've got your answer, the sum of this geometric series. If x to the power 6 is equal to 3, determine the value of the following. So what is the answer of the following expression? Okay, so I did this question in 2 ways, and I'm going to show you both methods to get to this answer. What I did first is I kind of took the x to the power 6 equal to 3 and I changed it slightly just to have a look at, how can we manipulate this a little bit. So if I raise all of this to the power of 3, then 3 to the power 3 is going to be 27, and 6 times 3 is going to be x to the power 18. So I know that x to the power 6 is going to be 3, and I know that x to the power 18 is going to be 27. Now, looking at what they gave me, I can definitely take out a highest common factor from this massive expression here, because x to the power 18 will be able to divide into all of these terms. So I took that x to the power 18 out of this bracket, and then I've got 1 plus x, and then all of those will be like 18 less. So your last term, if you take 18 x's out, there will only be 5 x's left. And we are going to use substitution now. I know that x to the power 18 is 27. I worked that out earlier. So I'm going to substitute that in to my x to the power 18. What I do then is I'm going to get the sum of this. Okay, so this is a series. We call this a geometric series. How do I know this is geometric? Because I'm timesing by x every time. Times by x, times by x. So you get x squared, then x cubed. So we have a constant ratio that is that's occurring here. So I know that this is a geometric sum, And to get the geometric sum, I also know the formula by now. So the first method that I'm showing you here is where we are using the formula of a geometric sum to simplify this expression. And what I did here was, to get this answer, I wanted the first term. The first term here is 1, so you can see that's 1 there. R is your common ratio, which is x. N is the amount of terms, so it's how many of these do I have to add. Okay, so you can see, remember, this is not the 5th term, this is actually the 6th term if you go and add all of them together. So this is x squared, x cubed, and x to the power 4. So all of those are still in between. So that's 4, 5, 6. So there's six numbers to add. Minus 1 is part of the formula, and your common ratio again is x minus 1. So this whole red bracket here becomes the formula of the geometric series. Then what I did next, you will see that this is a denominator, this is a numerator, so we can cancel off the x minus 1s immediately, and you are then left with something very simple to simplify, 27 with x to the power 6 minus 1 inside the bracket, and we've got an answer for x to the power 6. That was 3. So if you sub 3 into x to the power 6, you can simplify that to get your final answer of 54. Now I'm going to do this in another way, just so that if you don't remember this formula for some reason, then you can still actually work it out. So this is the other method. And I kind of started again in the middle of the example where I've already subbed in my 27. So that's still, I'm doing the highest common factor thing there. Substituting in x to the power 18, which I worked out was 27. And then I wrote out all of these terms that are left. And then what we do is we have to times this out. So this is just, it takes very long, but the 27 I'm going to write in front, and then this x will be timesed with every single term in that bracket. And that's what I did here. So I said x times 1 is x. X times x is x squared. And I did that for all of them up to x to the power 6. Then you take the next number. The next number in this term is negative 1. And then you start timesing that into this bracket. So negative 1 times 1 is negative 1. Negative 1 times x is negative x. And I did that for all of them. And then you will see that you get like terms that can cancel, and which I already cancelled off for you. So you can see there's an x minus x. X squared minus x squared. So I cancelled all the terms, and the only thing that you've got left will be x to the power 6 and minus 1. And that is what's left in the bracket, which is what I ended off with anyway with the method 1. X to the power 6, we know that is 3, so you sub that in. Finally, you just work that out and you get the same answer of 54. And then for our last question for this session. In the diagram on the left, there are 14 squares of all sizes. What is the total number of squares of all sizes on the board on the right? Now, we are going to do this with trial and error. There is actually a formula that you can use when you get problems like these, but we are not going to cover that formula. We are going to leave that for your senior maths Olympiads. So in this case, we are going to go and work this out by ourselves. And we are going to start by looking at this diagram, and we want to go and see how many squares do I have in this whole thing where I have a 1 by 1 square. And a 1 by 1 square is exactly that little block there. That's one little 1 by 1 square. So how many squares do I have in there? Now, if you want a quick way to work it out, you can just see, how many squares do I have horizontally and how many squares do I have vertically. So that's 6 times 6. So that's going to give me 36 squares. So that's the first bit. There's going to be 36 small little 1 by 1 squares. Okay, let's erase. We now want to go and look for all the 2 by 2 squares. So let me draw the first one out for you. There's a 2 by 2 square. That's my first 2 by 2 square. Then this can also be a 2 by 2 square. And I can have another 2. So this is going to take me forever. Now, a quicker way to do this, instead of writing all of them out, is to look at the center. You see, that center is going to give me one 2 by 2 square. So instead of looking at the sides, let's erase the sides. Let's just look at the center of all the 2 by 2 squares and let's go count them off. So we've got a center there, we've got a center there and there and there. Then we'll have another few here. And we'll have more there. Okay, let's fill all of them in. So these are all the centers of possible 2 by 2 squares. And that is my last one. So how many dots do I have? That's how many squares you will have. So the amount of dots there, if you count them, 1, 2, 3, 4, 5, 5 times 5. So that is going to give us 25 2 by 2 squares. Let's start again. Now we want 3 by 3 squares. Now I'm going to draw out the first one. So that's 3 by 3. I just want to find the middle, you see. So that's going to be the middle of a 3 by 3 square. Which means that can also be a middle. That can be a middle. And that can be a middle. As will these ones. So I'm marking off all the middles of possible 3 by 3 squares. And that's it. So that's 4 by 4. So that's going to be 16 squares. 16 squares of 4 by 4. 3 by 3. Okay. Now we are moving to the 4 by 4 squares. So let's draw out one of them. So that's 4 squares. That's 4 squares. Let's check out where will the middle be of one of these. And that's going to be right there. Okay, so we'll have one there. We'll have one possible one there, yes. And I think that's about it. Then we'll have one there, one there, one there. There, there, there. And that's it. I mean, if we move a center there, it's not going to fit in. So that's 3 by 3. So that's going to give me 9. Okay, so here we get 9 4 by 4 squares. Almost done. We now want to check how many 5 by 5 squares can we fit into this diagram. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Close off. And do we have a center here? Actually, this one's quite easy to see. I mean, you're going to have one there. Then you're going to have one in this corner. You can have one in this corner. And you can have another one in that corner. So that's just 4. There's 4 possible 5 by 5 squares. 4 squares there. And then finally, how many 6 by 6 squares do we have? There's only one. Only one of them. So in total, how many squares can I fit in here? So if I add all of this together, so we've got 36 plus 25 plus 16 plus 9 plus 4 plus 1. That will give me my total amount of squares that I can fit into that diagram. And that would be 91. 91 squares. So remember this method. Looking for the centers definitely helps you to get to all the possible squares with a certain size.